How are you all doing this morning? Good.
Doing pretty well.
Good morning.
Fantastic. So today we are going to talk about the transient analysis of RC circuits. So let's consider a simple circuit containing some source voltage Vs, switch that is going to open at t is equal to 0, and it is connected to a resistor and a capacitor, like so. And let's say that our voltage drop over our resistor will have this polarity. Let's call it VR as a function of time. And our capacitor will have a similar voltage, VC, as a function of time. And let's see. We may also have some capacitor like so. And some resistor current, IR of t, flowing around. Right. So at time t is equal to 0 minus, immediately before our switch changes states, our circuit is going to look like this, right? We have some voltage source Vs. Because our switch is closed, it's going to look like a short circuit. Then we have our resistor and our capacitor. Because we are at DC steady state, is going to look like an open circuit. So this would be IR at 0 minus. In turn, this would be IC at 0 minus. Here's our voltage VR at 0 minus. And here's our capacitor voltage VC at 0 minus. So it should be pretty easy to see that our capacitor voltage at t is equal to 0 minus will just be our source voltage Vs. And so what this means is that our capacitor has some amount of energy stored within it up until the point that the switch opens up. Once the switch opens and the voltage source Vs is removed, so we could call that at t greater than 0 plus, our circuit is going to look like this. Right? And so what's going to happen is that the capacitor is going to start transferring its stored energy to the resistor until the voltage drop across the capacitor reaches zero, which will occur when all of the energy stored by the capacitor has been converted to heat by the resistor. So we have an extraordinarily similar situation as to what we saw in our RL circuits on Tuesday. So during the transient condition, which means T greater than 0 plus, we can write a Kirchhoff's current law equation that says IR of T plus IC of T is equal to 0, because we know that Kirchhoff's current law has to be satisfied for all points in time. Otherwise, our circuit is violating the law of conservation of charge. We can express IR of T and IC of T in terms of our capacitor voltage, right? So we can easily see that VR of T and VC of T really represent the same quantities. So our voltage drop over our resistor, or excuse me, our current flowing through our resistor could be represented by the voltage drop over our capacitor, and we obviously know that the current flowing through our capacitor can easily be related to the voltage drop over our capacitor as well. So using Ohm's law, we're going to have 1 over R times VC of T plus C dVC by dt is equal to 0. And we again have a homogeneous first order linear differential equation. So when we dealt with our inductor problems on Tuesday, we guessed that our current waveform was of the form A, E, the ST, and we'll do the same here because we have the same type of equation, so it seems reasonable that it'll have a similar solution. So when we substitute in that guess value, we wind up getting 1 over R times AE to the ST plus C times the derivative of AE to the ST is equal to 0, which is going to look like 1 over R times AE to the ST plus SC AE to the ST is equal to 0. And now we can group like terms. So we would get A times 1 over R plus SC E to the ST is equal to 0. And exactly as we observed before, if A is 0, that is a trivial solution where it effectively means that our voltage source is supplying 0 volts so that there's no energy storage that we've had to accommodate for in any way, shape, or form. E to the ST can never reach exactly 0. It can only get close for negative values of S as time progresses. And so we have this characteristic equation here that's the part that's going to be 0 for specific values of R and C. So if we have 1 over R plus SC is equal to 0, and we solve this guy for S, what we should find is that we get negative 1 over RC, if I've done my math correctly here. And I believe I have. All right. So that means that we can now say V of t will be of the form AE to the negative t over RC for all our capacitors. And since we know how the circuit behaved at t is equal to 0 minus, we could, so what I'm saying is that we could easily analyze this circuit and figure out what was going on at t is equal to 0 minus. And we know that the capacitor voltage cannot change abruptly. We know that A has to be VC at 0, giving us VC of t will always be of the form, assuming that we're taking our sources out of our system, VC at 0, e to the negative t divided by RC. So we have an extremely similar.
Dr. Hartman,
Ma'am.
will you explain one more time why A equals VC at 0?
Absolutely. Okay. So if we analyze this circuit that I've drawn at t is equal to 0 minus, right? We find that VC at 0 minus has some specific value. In this case, it would be VS. Do you agree with that?
Yes, sir.
All right. Because the capacitor voltage cannot change abruptly, VC at 0 plus has to be the exact same as VC at 0 minus. If they are different values for the same instant in time, effectively, that means that an infinite transfer of energy has occurred in an infinitely small amount of time, which would
That's not
violate all the laws of physics.
yeah.
Right. So what that means is that when we evaluate this guy right here at exactly t is equal to 0, it has to be the same as the voltage we saw at t is equal to 0 minus. And the only way that occurs is if A is exactly equal to VC of 0.
Okie dokie.
All right, so we now have the framework by which to solve really any RC circuit, just like we did our LC circuits. So what we should observe in any RC circuit is that Y of t, which could be representative of any voltage or current in an RC system, will be of the form Y at 0 minus for t less than 0 minus, and Y at 0 plus e to the negative t divided by RC, all t greater than 0 plus. So it has the exact same form as what we developed for our inductor circuits on Tuesday, except that our time quantity in the exponential is multiplied by a slightly different factor. And we're going to resolve that portion of it a little bit later on today. But before we do that, let's look at a couple of example problems. So let's say that we have the following circuit where we have a 50 kilo ohm resistor, a 10 millifarad capacitor, and our switch is closed at terminal B before changing over to terminal A at t is equal to 0. Then we have a 20 kilo ohm resistor and a 10 volt source like so. And our quantities of interest will be VC of T and IC of T. Okay. So this is a transient analysis problem. Let's just talk our way through what's going on here because it looks a little different than what we've done previously, right? Before we directly switched the sources off, here we're switching what the capacitor is connected to, but it's effectively performing the exact same function, right? So at T is equal to 0 minus and prior to that point in time, we have our voltage source connected to a resistor connected to the capacitor, and we can easily infer that some energy should be stored in the capacitor. At T is equal to 0, that switch changes positions and the capacitor is instantaneously disconnected from that source network and connected instead to that single 50 kilo ohm capacitor, or excuse me, 50 kilo ohm resistor, leaving us with a simple RC network where we're trying to find out what the voltage signal and current signal behave like after the switch closes. So we'll analyze this in effectively the exact same way that we did on Tuesday, right? Step one, we'll analyze the circuit at T is equal to 0 minus. So at T is equal to 0 minus, this guy is going to look like this. We have our 50 kilo ohm resistor that isn't really connected to anything. Then we're going to have our capacitor, and our capacitor is being represented by an open circuit because we're at DC steady state. So this is our capacitor voltage VC at 0 minus. Here's our capacitor current IC at 0 minus. Then we have our 20 kilo ohm resistor and our 10 volt source. So let me start by asking you guys, does the way that I've redrawn this circuit for specifically T is equal to 0 minus make sense?
Yes.
Yeah.
All right. So we need to determine the quantities VC at 0 minus and IC at 0 minus in order to use our general equation to determine our correct answer at the end. So what can somebody tell me about either of these values?
Would the current flowing through the 20 ohm be the same thing as IC since they're connected in series?
Absolutely. So what's the current flowing through the 20 ohm resistor? 20 kilo ohm resistor.
500. Wait. 10 divided by 20. That'd be just like 5 milliamps, 0.5 milliamps.
I disagree.
How?
Okay. Is the 20 kilo ohm resistor part of a closed current carrying circuit?
No.
Okay.
I mean, you got an open circuit right there where VC is, and you also have another open circuit separating that and the 50 ohm resistor, or 50 kilo ohm resistor, correct?
Correct. So how can any current be flowing through the 20 kilo ohm resistor if the 20 kilo ohm resistor isn't part of a closed current carrying path?
So the current would just be 0.
Exactly right. We should observe that the current flowing through a capacitor at any time prior to our switch opening up, so the current flowing through a capacitor at DC steady state will always be 0 amps because it represents the current flowing through an open circuit. Make sense?
Yeah.
All right, so what can we say about the voltage now? Acknowledging that the current flowing through the 20 kilo ohm resistor is the same as the current flowing through the capacitor, which means that there's no voltage drop across that 20 kilo ohm resistor.
If there's no voltage through the 20 kilo ohm, would it just be the same as 10 volts?
Exactly right. So simple application of Kirchhoff's voltage law. If we know that this voltage is 0, simple application of Kirchhoff's voltage law tells us that VC has to be equal to 10 volts. So I believe that we have completed our circuit analysis at t is equal to 0 minus. But if there's any questions or anything, I'd be happy to answer them. If not, we'll move along and look at the circuit at t is equal to 0 plus. So anybody got any questions?
Is that current that you said that current's always going to be 0 amps, correct?
Yes, the current flowing through the capacitor at any time when the capacitor is at DC steady state, meaning that we're treating it like an open circuit, it will always be 0 amps.
Okay.
Any other questions? All right. So now we're going to analyze the circuit at t is equal to 0 plus. So at t is equal to 0 plus, our switch is moving from position or being closed at position B to being closed at position A. And so what that means is that our 10 millifarad capacitor is now being connected to our 50 kilo ohm resistor, and that 20 kilo ohm resistor is effectively being open circuited. So it's no longer connected to the capacitor at all. So what that would look like would be something like this. So we have our 50 kilo ohm resistor connected to our capacitor. Here's our 20 kilo ohm resistor. Here's our 10 volt source. And let's see, what value? 10 millifarads. So here's our capacitor voltage, VC at 0 plus. Here's our capacitor current, IC at 0 plus. And we're trying to determine those two quantities. So let's start with our capacitor voltage, okay? We know that the capacitor voltage cannot change abruptly. So what that means is that whatever value the capacitor voltage had at t is equal to 0 minus, it must still have at t is equal to 0 plus. VC at 0 plus has to be 10 volts.
So for capacitors, you're saying that the voltage can't change abruptly, but for inductors, the current can't change abruptly, correct?
That is exactly right.
Okay, I had it backwards then, my bad.
Yep, not a problem. So what I can do to slightly redraw this circuit is the following. You don't have to do it this way. This is just my preference. we can actually replace our capacitor with a voltage source. Okay. And we can do that because we know that the capacitor voltage will have this exact value at this instant in time, right? At the instant in time where that switch opened up, or switch changed positions in this case, the capacitor voltage must be 10 volts, and the amount of current flowing through the capacitor can be whatever it needs to be to make the circuit operate. So I'm replacing my capacitor at this instant in time with a 10 volt source because I know that the capacitor voltage is 10 volts, having the same polarity, so positive polarity on top, negative polarity on bottom, that our capacitor voltage is defined to have. So this is analogous to when I was replacing my inductor with a current source at t is equal to 0 plus in our circuits that we analyzed on Tuesday. I still have my unknown IC at 0 plus that I'm trying to figure out. And the rest of my circuit, so my open circuit with my 20 kilo ohm resistor and 10 volt source is still over here. The only change that I've made is I'm replacing my capacitor with an electrically equivalent independent voltage source at this one specific instant in time. So with that in mind, how could I go about determining that quantity IC at 0 plus?
Could you just analyze that left hand of the circuit using like KCL? Or you could probably do current or probably do voltage division to find the voltage across that 1050 kilo ohm.
Is voltage division necessary? I would
No,
argue,
it's all in parallel, so wouldn't it just be 10 volts?
right, but I'm trying to find the current. We've established that the voltage has to be 10 volts because the voltage can't change abruptly. So your initial thought about doing Kirchhoff's current law, while that's not where I would go, it is actually kind of useful to explain what's going on here, right? So if we use Kirchhoff's current law, which says that the current IC would be equal to the current flowing to the right plus the current flowing to the left, well, we know the current flowing to the right is exactly 0 amps because there's an open circuit in that path. So no current can flow in that direction. So all of our capacitor current is going to wind up flowing through that 50 kilo ohm resistor. So to me, that means that the current being flowing through our capacitor, IC, is going to be 10 volts divided by 50 kilo ohms. But I need to pay attention to the fact that the current is leaving the positive polarity terminal. Or another way to think of it is the current is entering the negative polarity terminal of the voltage source. So I'm going to put a negative sign right here to accommodate for that. And so when I divide 10 volts by 50 kilo ohms, I get negative 0.2 milliamps. Does the analysis I've done there for determining IC make sense to you guys?
Yes, sir.
All righty. So now we are ready for step 3, unless anybody has any questions about the analysis that we've done, which you just said makes sense. So step 3 is put our results to our equation. So for our capacitor voltage, VC of t, we will have the general form VC at 0 minus, t less than 0 minus, and VC at 0 plus e to the minus t divided by RC, t greater than 0 plus. So to me, that's going to give us 10 volts for t less than 0 minus, and 10 e to the negative t divided by. So what resistor should we be using here?
The 50 kilo ohm.
50 kilo ohm, exactly right, because that's the only resistor that's connected to our capacitor during the transient condition. And then we have our capacitor value itself, which I keep forgetting because it never 10 millifarads. For t greater than 0 plus. And now I'm just going to do that math of, so let's see, 10 volts for t less than 0 minus 10 e to the negative. All right, so I have 1 divided by 50,000 times 10 times 10 to the minus 3. So that looks like 1 over 500. And so what I'm going to do is I'm going to take the reciprocal of that. So that's going to be e to the minus 500t. Is everybody okay with what I've just done?
Yeah.
Please, so.
All right. I like to express my answer as e to the something t, and I don't particularly enjoy using fractions, so that's why I did it that way. So this quantity right here, this 500, is exactly 1 over RC. I could also see then that my capacitor current, IC of t, using our same generic formula, is going to be 0 amps for t is less than 0 minus, and it will be negative 0.2 e to the minus 500t milliamps for t greater than 0 plus. So I just want to point out something here that I don't think I brought up Tuesday. Our voltage is obviously a continuous function. It's 10 volts for all time less than 0 minus, and then it's 10 volts at exactly t is equal to 0 minus, and 10 volts at t is exactly equal to 0 plus, after which point it starts to exponentially decay. Our current in this case is discontinuous, meaning it's 0 amps, and then at the same instant in time at t is equal to 0, it's also negative 0.2 milliamps. That's perfectly okay for the capacitor current to change abruptly. It's only the capacitor voltage that cannot change abruptly. Similarly, if we had an RL circuit, as long as the inductor current is continuous, the inductor voltage can change abruptly all day, and it's really no issue whatsoever. So let's look at another example problem. So let's say we have 200 milliamp current source connected to a 300 ohm resistor. We have a switch. I don't like the look of that. That will be opening at t is equal to 0. And then here we have a 100 ohm resistor. A 300 ohm resistor. And then a 6 microfarad capacitor over which a voltage drop Vc of t occurs. And I want us to also find this voltage drop Vr of t. All right. So this is our new circuit of interest. So what should step 1 be?
Analyze at t equals 0 minus. That's it.
Absolutely correct. Analyze at t is equal to 0 minus. So at t is equal to 0 minus for this circuit, our switch is closed. So we would have our 200 milliamp current source connected to that 300 ohm resistor. Then we would have our 100 ohm resistor over which that voltage VR at 0 minus occurs. Here we have an additional 300 ohm resistor. And then these are the open circuit terminals of our capacitor, because at DC steady state, the capacitor looks like an open circuit. So how can I figure out what either of those quantities at t is equal to 0 minus should be?
Just wondering if, could you possibly do a source transformation on the left side, and since that would be in parallel with the VR, or no?
So you are suggesting that I convert that 2 milliamp source that is in parallel with the 300 ohm resistor into a voltage source in series with a 300 milliohm resistor. Is that correct?
I don't think it's going to work.
Oh no, it'll absolutely work.
It will? Okay.
Yeah, let's do that. That's not the way that I would do it, but we can absolutely do it that way. So if we do source transformation, we'll have a voltage source that we will need to figure out what voltage is being supplied by it in series with a 300 ohm resistor. And then that is going to be connected to a 100 ohm resistor here. Here's our voltage VR at 0 minus. Here is our other 300 ohm resistor. Here is our voltage VC at 0 minus. So since you suggested doing a source transformation, please tell me what value of voltage my voltage source should have.
Is that supposed to be 200 milliamps or 2 milliamps? Just curious.
Oh, I'm sorry, it is 200 milliamps. Thank you. That's my fault. So what do I do to get that voltage doing source transformation?
Multiply the resistor and the current source together.
All right, so that would be 200 milliamps times 300 ohms, so 0.2 times, sorry. Trying to get rid of, I mean, I feel like I should be able to do that in my head. It'll be like 60 volts or something like that, but I just want to make sure. 0.2 amps times 300, yeah, 60 volts. All right. So now what could I do to determine VR or VC?
Could you possibly do maybe KVL?
Yes, so which loop do you want to do KVL for? There are 3 potential Kirchhoff's voltage law loops that I can see. We could do one around the left-hand loop, one around the right-hand loop, or one around the outside of the circuit.
I'd probably just say the left one.
Okay, so if we do KVL, I'm going to write KVL at the left-hand loop. We would have negative 60 volts plus 300 ohms times the current flowing through that 300 ohm resistor, which we don't know. I'm just going to label that as I300 for right now. And so I'm going to draw this and call it I300 to be clear about what we're finding. Plus VR at 0 minus is equal to 0. So this equation gives us 2 unknowns. So we would need to either be able to solve for I300 or VR in order to solve this guy. And if we could solve for VR, then we're done. So what would we do next?
You can solve for I300
How?
just doing your voltage divided by resistance, and that gives you the current flowing through there.
So you're saying that 60 volts divided by 300 ohms gives me I300?
Yeah.
I disagree.
Why? Because
If
like
we do
it's right
that-
there, so it shouldn't the total current leaving that 60 volts give you that?
So if we divide 60 volts by 300 ohms, that is us saying that there is a 60 volt drop over the 300 ohm resistor, which would imply that this terminal right here is at 0 volts. That would in turn imply that the voltage drop over our 100 ohm resistor is also 0 volts, which we have no reason to make that assumption. So let's look at this in a slightly different way. We're gonna keep on doing what we're doing. It's perfectly okay. But let me ask you guys a question. That current I300 using Kirchhoff's voltage law, or excuse me, Kirchhoff's current law, will be the current flowing to the right through this 300 ohm resistor, plus the current flowing down through this 100 ohm resistor, correct? That's how Kirchhoff's current law works. Everybody okay with me thus far?
Yes, sir.
All right, what's the current flowing to the right through the rightmost 300 ohm resistor?
You mean like the one that's going through the 300 ohm?
The one in red that's going through the 300 ohm, yes.
Yeah, it wouldn't be anything because it's not ground. It's not in a completed loop.
Exactly right. Which means this current right here is also I300 using Kirchhoff's current law, right? I'm effectively proving that no current can split off, and so all of the current that's leaving that source flows through that left 300 ohm resistor, and then it turns down and flows through that 100 ohm resistor. So we could see pretty easily then that I300 is going to be 60 volts divided by 400 ohms. Which would be 3/20 or 150 milliamps, I believe. Yeah. And making that substitution into our equation, we would find that VR at 0 minus, so let's see, 60 minus 300 times 0.15 would be 15 volts. Does that analysis make sense?
Yes.
Okay, now let's talk about how we could do it in two easier ways, or to me, two easier ways. Since we know that no current can split off and flow through the 300 ohm resistor to the right, that means that that 60 volt source just sees the 300 ohm resistor to the left and the 100 ohm resistor connected in series. So I would argue that we could get that same result using voltage division, right? So we could say that VR at 0 minus is 60 volts times 100 ohms over 100 ohms plus 300 ohms, which will turn out to be 60 times 1/4 is 15 volts. There is a third way to look at this without doing the source transformation at all. So I would argue that using Ohm's law, we could say that VR at 0 minus is equal to 200 milliamps times the parallel combination of the 300 ohm resistor and the 100 ohm resistor. And if we do the math on this guy, so that's 200 times 0.2 times 300 times 100 divided by 400 also gives us 15 volts. All of these methods that we've talked about are perfectly fine, but I would argue that the Ohm's law one is the most efficient because we didn't have to do a transformation and we get the answer in exactly one step. So do you guys see why we can apply Ohm's law there?
Not very clearly.
All right, let me redraw the circuit then. What we have is a 200 milliamp source connected in parallel to a 300 ohm resistor connected in parallel to a 100 ohm resistor, and we want to know this voltage, right? We know that since that 300 ohm resistor here isn't part of a closed current carrying loop, it's not going to contribute anything at all. So that's why I've effectively just thrown it away for this part right here, okay? This Vx, another way that we could do this is call it VR at 0 minus. So does this representation of our situation make sense? Let's start there.
Yes, sir.
So I have a known amount of current flowing into two resistors in parallel, and I just want to know the voltage drop over the two resistors in parallel. So I'm just multiplying that current by the equivalent resistance.
Gotcha.
So we've looked at multiple different ways that we could consider this circuit. And again, there's nothing wrong with doing the Kirchhoff voltage law that we did originally, recognizing that none of the current can split off and flow to the right. And then so just writing that simple KVL loop around that left-hand side, substituting in the value of the current and then calculating that voltage. Nothing wrong with that at all, but that was like 4 steps. The voltage division method was doing the source transformation and then doing voltage division, 2 steps. And then Ohm's law is 1 step. All of them are equally valid, but one of them is a more efficient means by which to solve. Okay, so you should be looking for efficiency as well as just how to do it. And it just takes training and looking at a bunch of these guys to be able to get to that point. So definitely work with what you're comfortable with, but kind of always be on the lookout for little shortcuts here and there if at all possible. Okay. So I think that we have beaten that resistor voltage to death. So we know 3 different ways that it's 15 volts. How does that help us determine our capacitor voltage?
Well, since there's no current flowing through that 300 ohm resistor, wouldn't the voltage at that resistance, that 100 ohm resistor, be the same voltage at VC?
Exactly correct. So because we know that the voltage drop across this 300 ohm resistor has to equal 0 volts because this current is 0 amps, VR at 0 minus and VC at 0 minus are the exact same thing. So this guy has to be 15 volts as well. Very good job analyzing that. So I'm sorry, go ahead.
I'm very sorry. I know that what Dylan said was the smart and educated answer, but I connected those two because I was like, oh, it's KVL. It's the only thing that could be equal to each other. Would that be a correct assumption, or am I just thinking about this wrong?
No, Kirchhoff's voltage law is absolutely correct. So let me sneak one in here in green. Right here. I think that'll give me enough room. Let's see. So we could say that negative VR at 0 minus plus 300 ohms times the current flowing through that 300 ohm resistor, which is 0 amps, plus VC at 0 minus is equal to 0, which would tell us that VC at 0 minus is exactly equal to VR at 0 minus.
Cool beans.
Yeah, so using Kirchhoff's voltage law is just what Dylan said is shorthand notation for using KVL around that right-hand loop effectively. So they're representing the exact same thing in the exact same way. He just did it slightly more intuitively, but it literally means the exact same thing.
All right.
All right, so are we good to move on to T is equal to 0 plus?
All good.
All right, so let's do that on down here. Oops, that's too much. So our second step analyze the circuit at T is equal to 0 plus. So at T is equal to 0 plus, our switch has opened up So that means we're going to have our 200 milliamp source in parallel with a 300 ohm resistor. We have an open circuit here. We have our 100 ohm resistor over which we're trying to find VR of 0 plus. We have our 300 ohm resistor here. And I'm going to do what I did like in the last problem. And I'm going to express my capacitor as a independent DC voltage source at this specific instant in time. So it'll have the same polarity as my capacitor voltage. So positive polarity on top, negative polarity on bottom. And it will also have the same voltage as my capacitor voltage. So this is my way of saying that VC at 0 plus has to be 15 volts because VC at 0 minus was 15 volts. And we know that the capacitor voltage cannot change abruptly. So how could we figure out VR at t is equal to 0 plus?
You just do voltage division.
Okay, so I think I got enough room here. So that would be 15 volts times 100 over 400. So 15 over 4 would be 3.7 volts, right?
Yeah.
Does anybody have any problems with that methodology of the circuit analysis? All right, that's exactly what I would have done as well. So let's move along to putting stuff into our equations. But so step 3. So we are going to need to know the equivalent resistance that the capacitor sees, right? In a previous problem, there was only one resistor connected to the capacitor, so that was pretty trivial. So let's formally talk about how we find that equivalent resistance, okay? So as we discussed in class last Tuesday, we are looking for the Thevenin equivalent resistance connected to our capacitor, which means we need to be looking at a dead network during the transient condition. So I'm going to write here specifically for a dead network, meaning that we've turned off our independent sources. During the transient, our circuit looks like this. So our current source is turned off. So that's why it's an open circuit. We have our 300 ohm resistor on the left. Since we're during the transient condition, our switch is open. We have our 100 ohm resistor, our 300 ohm resistor. And because we're looking at this from the perspective of the capacitor, we take the capacitor out of our circuit and we look in through the terminals left by the capacitor. So this is the Thevenin equivalent resistance that we're trying to find. What should it be?
Should just be 400.
Exactly right. 300 ohms in series with 100 ohms. Absolutely perfect. Does everybody see that?
Yes, sir.
All righty. So now I'm going to go ahead and calculate 1 divided by RC. So that's going to be 1 over 400 ohms. And then I had 10 millifarad? 6 microfarad, right? Scroll all the way back up here. Yeah. 6 microfarad. What that's going to give me is, let's see, 1 over 400 times 6 times 10 to the minus 6. 1,250 over 3. 416.667. So from that, VC of T. So what value did VC have at T is equal to 0 minus?
15 volts.
All right, so this will be 15 volts for T less than 0 minus, and 15 e to the minus 416.667 T volts for T greater than 0 plus. That's literally just plugging the stuff into my general equation. For my resistor voltage, that would be 15 volts at T is equal to 0 minus. So 15 T less than 0 minus. And then here we would have VR at 0 plus, which was 3.75 e to the minus 416.667 T volts for T greater than 0 plus. Make sense? For this particular problem, we could have actually not even bothered keeping track of what was going on with VR until the very end, because we can see pretty easily for all T greater than 0 plus, we just have a simple voltage divider circuit that we would have needed to analyze. So that would be another methodology for working this type of problem. But I think that personally, having a generic catch-all equation works best for me and typically works best for the student, so that if you can do this simple, or what's intended to be simple DC circuit analysis at T is equal to 0 minus and T is equal to 0 plus, and just throw stuff into the equation and get the right answer, why wouldn't you do it that way? So does anybody have any questions about our solution for these RC circuits?
Are you gonna always have to use the Thevenin to solve these every time, or not all?
If there's more than one resistor connected to the capacitor for an RC circuit, or for the inductor, or more than one resistor connected to the inductor for an RL circuit, then technically yes, you'll always be finding that Thevenin resistance. But a lot of times, like doing this explicitly was probably overkill. And what I mean by that is when we're looking at this 15 volt guy is connected to, is representing our capacitor, we can easily see that it's just the 300 ohm resistor in series with the 100 ohm resistor. That's the only resistors that are actually connected to the capacitor. So the Thevenin method that I just used is a more formal version of doing it by inspection. If you do the Thevenin method, you can't get it wrong unless you don't apply things correctly. But in the overwhelming majority of circuits that we're going to look at, you can do it by inspection.
Okay, thank you.
Any other questions? All right, so the last thing that I would like to talk about today is the concept of a time constant. All right, so for RL circuits, we developed a generic equation that said that y of t was equal to y at 0 minus for all t less than 0 minus, and it was equal to y at 0 plus e to the minus r over L t for t greater than 0 plus. Similarly, we said that for RC circuits, y of t is equal to y at 0 minus for t less than 0 minus, and y at 0 plus times e to the minus t over RC for t greater than 0 plus. So hopefully it's fairly obvious that these two general equations for the response of an RC circuit and an RL circuit are extremely similar to each other. The only difference between the two of them is the factor that's multiplying time in the exponential function. Okay. So what electrical engineers have done is they have gotten lazy and developed a quantity called the time constant, where the time constant is y of tau, where tau is the time constant, is exactly equal to y at 0 plus times e to the minus 1. Okay, so what this means is that the time constant tau is equal to L over R for RL circuits, and tau is equal to R times C for RC circuits. And this quantity lets us write a single generic equation, y of t is equal to y at 0 minus for t less than 0 minus, and y at 0 plus e to the negative t divided by tau for t greater than 0 plus, so that we can work any first order transient analysis problem, be it an RL circuit or an RC circuit, using the following 4 steps. 1, analyze the circuit at t is equal to 0 minus. 2, analyze the circuit t is equal to 0 plus. 3, calculate the time constant tau. And 4, put results into the general equation. So those are going to be our 4 steps going forward. I'd like to talk a little bit more about what the time constant represents, though. Okay. So we have, in general now, an expression y of t is equal to y of 0 plus e to the minus t over tau. So what tau is representative of is the rate of decay for the system. And it doesn't really care whether it's an RL system or an RC system. So for instance, if we had let's talk about an RL circuit, okay? So for a generic RL circuit, I'm just going to call this 100 ohms for the sake of argument. let's call this guy 10 kilo ohms. And this guy 5 henries. It is going to behave the exact same way as this circuit. I'll leave that as 100 ohms. So it's going to behave at the same rate, but if I change that value, it's going to mess with things technically. $100 kilo ohms. And 50 henries. And I could, if I wanted to go through and actually do a little bit of math, draw a representative circuit containing a capacitor that behaves identically to that inductor circuit, okay? So all our time constant really does is just quantify how quickly our signal decays, right? So if we have graphically a current that we are interested in, and it has some initial value, let's call this I at 0 minus like so. We know that is going to exponentially decay. Like so, where this curve would be represented by I at 0 plus e to the minus t over tau. Well, in exactly one time constant, let's call this 1 tau here, it has decayed to, I think it's 37%, but let me just double check here, e to the minus 1. Yeah. 36.8% of its original value, and 2 time constants. So roughly here. It's down to 13.5%, right? So just to be clear here, this is e to the minus 1, this is e to the minus 2, and so forth. And what we'll find is that at 5 time constants, where we have e to the minus 5, our signal has decayed down to less than 1% of its original value. So you may recall on Tuesday's lecture when I talked about how our signal decays to 0 at infinity. Well, for an engineer, infinity is 5 time constants. The signal has gotten so small in comparison to its initial value that we can treat it as if it were 0%. Okay, so time constants, again, quantify the rate of decay of the system, and they also let us know how long it takes our system to fully charge or fully discharge. And that amount of time is commonly accepted to be 5 time constants. So I'm going to do one of the experiments probably sometime this weekend, and I'm going to pay some attention to making a video that legitimately shows you, if we have a system, it takes roughly 5 time constants for it to fully discharge and another 5 time constants for it to fully charge. And I'll show you what happens if we don't allow the system that 5 time constants to fully charge or discharge. It actually messes up all of our analysis. So just to reiterate, for engineers, 5 tau is approximately infinity. That is literally something I ask very regularly on your exams. Or I might ask, how many time constant does it take a signal to decay to less than, say, 25% of its initial value? That would be 2 time constants. Those are all just figured out by doing e to the 1, e to the -1, e to the -2, etc. Nothing remotely difficult there. And the time constant for an RL circuit is L over R. The time constant for an RC circuit is just R times C. And from here on out, we're going to be using this generic expression for what's going on for t greater than 0 plus. All right. So that's all that I had prepared for today. Do you guys have any further questions to ask of me? We still got 30 minutes left. I'm happy to stick around and answer any questions you've got.
I have a question from homework 11 that I couldn't figure out.
All right. Let me pull up homework 11 on my other computer real quick, and then we'll take a stab at it, okay?
Okay. It's problem number 1.
Number 1?
Yes, sir.
All right. Excuse me, web work.
Are we getting an equation sheet for like all this stuff? Just curious.
Typically, the answer would be no, but I will consider it because of the weird paradigm that we are in. I'm actually leaning more towards allowing you guys to have an equation sheet. My only concern is how to implement that over the online thing. So I need to figure out if there's a way that I can generate an equation sheet that it would allow you to look at while you're looking at the test, so that it doesn't constantly think you're cheating, if that makes sense.
You
Yes,
can
ma'am.
do that.
I know one thing that Dr. Swanbaum did for like a reference table for statics is he had an information tab, like in the lockdown browser, you can have like information tabs that's not an actual answer, like 1 through 10, and then an information tab. And that's what we use, because he also was trying to ensure that we didn't like have paper reference material that could be easily scribbled upon. So.
All right, so it sounds like I'm going to pop across the street and talk to Mikey at some point in the next couple of days and figure out how to do that.
Okay.
All right, so homework 11, problem 1. Okay. Let me get down to a fresh sheet of paper here. So in homework 11, problem 1, we have what appears to be a fairly ugly looking circuit. I'll take a moment to draw it out here. So let's see. So this guy is R6. This current is I2. This guy is V2, L1, R2, R5, V3, L2, R3. Then I have to draw the other half of the circuit as well. Here's R1, V1, L3. This guy is R4, and this voltage is defined to be Vx. And you are asked to determine, okay, so there was I2, this guy right here will be I1, and you want to find I1, I2, and Vx. Okay. So what is troubling you? Let's start there.
Well, so because the inductors, they when you're doing the circuit analysis, they would they would just be short circuited, right?
Absolutely right. This is a DC circuit, so literally all of our inductors will be shorts. So we can erase them and replace them with a wire.
So when I was trying to solve this one, I tried to use mesh, and I couldn't figure out where I was going wrong. I
All
tried it
right,
like 4 or 5 different times, and I kept getting the incorrect answers.
let's give it a stab here. So I'm going to call this guy R3, and I'm going to leave everything in symbols so that since it's going to be 4 meshes, we're going to wind up using MathCAD anyway. So you could literally just pop your numbers in and all that kind of stuff. So I've converted all of my inductances into short circuits because this is a DC circuit. Let's call this guy mesh 1. Actually, I lied. Let's not call it mesh 1 because we already have a current I1, so that's just going to be confusing. So let's call it mesh A, mesh B, mesh C, and mesh D. Sound reasonable?
Yes, sir.
All right, so there are no current sources in our system whatsoever, so we're not going to have to worry about applying super mesh and developing current relationships at all. We can literally just directly apply KVL for each mesh. So let's start at mesh 1. All right, so I'm going to start here, and I'm going to follow that mesh current around. So for this horizontal branch right here, we have no resistance or no voltage sources, so we don't really see anything. So now the next thing that we would see would be negative V2. Then we would have our resistor R1 multiplied by mesh current IA minus mesh current IC plus V1 is equal to 0. Does anybody have any problems with that KVL equation?
Looks good.
All right, so let's do mesh 2. So I'm going to start right here. So the first thing that I see is the positive polarity terminal of V2. So I'll have V2 plus, then I see the resistor R6, and it's only going to have a mesh current of IB flowing through it. Then I have, see the resistor R2, and it's going to have a total current of IB minus ID flowing through it. And I set this guy equal to 0. Any problems with this mesh equation?
No, that's basically how I set, or that's exactly how I set my first 2 up.
All right, so then let's look at KVL at mesh. Oh, sorry, I'm just calling these 1, 2, and 3 when it should be A, B, and C. I apologize. A, B, mesh, C. All right, so I'm going to start here at that bottom tip. So the first thing I see is R4. And R4 will have a mesh current of IC flowing through it. Then I see the negative polarity terminal of voltage source V1. Then I see resistor R1, where R1 will have a total current of IC minus IA flowing through it. Then I see resistor R3, which will have a total current of IC minus ID, flowing through it. And I set that guy equals 0. Any problems there?
No, sir.
All right, finally, I will have my KVL at mesh 4.
Mesh D.
And I'm going to start at this same, sorry, mesh D. I'm going to start at that same point. So the first thing I see is R3, where R3 will have a total current of ID minus IC flowing through it. Then I see R2, which will have a total current of ID minus IB. Then I see R5, which just has ID flowing through it. And then I see the negative polarity terminal of V3 first. So I have these 4 equations, and I would solve those guys. I can see that I1 is IA minus IB. I can see that I2 is simply IB. And I can see that Vx is just going to be R4 times IC.
So,
Actually, so let me make a correction here, because I can see on my computer screen that I gave the wrong polarity to Vx. So Vx, as it shows up on my computer screen, positive polarity on top, negative polarity on bottom, which would change that to negative R4 times IC. So I apologize for writing that down incorrectly, but I believe I got all my other polarities correct.
that's essentially, that's how I set it up. So
Um,
you had my KVL equations were this. Like that's how I did my KVL equations. I think where I messed up is while I was solving it, I solved mesh A and B for, like I put them in terms of ID and IC, and then plugged those into equations C and D to get a 2-system equation.
Oh, okay. Yeah. So substitutions like that, it is technically possible to do them correctly, but it's very, very difficult. Like I've had lots and lots of students try doing stuff like that, particularly once we get into steady state sinusoidal analysis, where we're setting up systems using complex numbers, and they try to do substitution to break it down into something that they can solve using their calculator, and it very, very rarely works out correctly. If you have a 4 mesh system like this, you should be using MathCAD to solve it, or some other computer algebra tool. Do you currently have MathCAD?
I do have MathCAD. I didn't think I would need it for this homework though.
I mean, if it's greater than 3 equations and 3 unknowns, I use MathCAD or something similar for everything, just to make sure that I'm not making a mistake. So those substitutions, I've just seen so many students get frustrated trying to doing it and getting the wrong answer that I don't even bother trying to do them anymore. I literally just rely on MathCAD for anything 4 equations, 4 unknowns or larger.
Okay. So you wouldn't throw something like this at us on like the test?
No.
Like, okay.
No, solving a system with 4 equations and 4 unknowns, I literally will never throw anything like that on the test at you. Now, I definitely might be enough of a jerk to throw it to where it looks like it's going to be 4 equations and 4 unknowns, but like what I would wind up doing would be something like this, except that you would have some current source IX here, which would eliminate one of your equations. Right? There's still 4 meshes, but you know that IA is exactly equal to IX, which means you really only have 3 unknown quantities. Something like that, absolutely, I will be a jerk and do it. Or I might give you a question where it would require the use of source transformation to make it into a 3 equation, 3 unknown system or something like that. But something where the only way to solve it is 4 equations and 4 unknowns, not a chance.
So there's nothing I can do to like just do this by hand like normally.
Kramer's rule, where you would involve taking the determinant of a 4x4 matrix, which is absolutely doable, but it is ludicrously tedious.
Okay, so MathCAD.
Yeah, so MathCAD. MathCAD is
Okay.
way, yeah, my first quarter teaching Circuits 1 way back in 2017, I went through using Kramer's rule and did up to the determinants of 5x5 matrices, and I thought my students were going to burn me at the stake. So
Cool.
it's definitely doable, but it's so wildly tedious. Just use MathCAD. You students have access to it for free for a reason.
All right. Thank you.
Any other questions? About what we've talked about today or the last couple of days or any of the homeworks or anything like that?
I have a question. It is related to circuits, but nothing we've spoken about.
Okay.
This is anyone who's like listening for pertinent information to go ahead and leave. I was talking to my dad, who is an actual electrician, and he said something about Eli the Iceman, because I was like talking about inductors and capacitors and how I'm kind of fuzzy on it. He was like, "Oh, do you know Eli the Iceman?" And I'm like, "No." And we spent 2 hours talking on it, and I still have no idea what he was talking about.
Okay, well, it makes perfect sense that you have no idea what he's talking about yet. Give me 2 weeks and it'll make perfect sense. And I will actually bring up the concept of Eli the Iceman.
Okay.
What
I was
Eli
like-
the Iceman is used for is determining whether the voltage or current is leading or lagging in a steady state sinusoidal system. We're not quite there. Steady state sinusoidal systems is, once we take exam 2, we do a review of complex numbers, a review of sinusoidal signals, and then literally everything else is steady state sinusoidal circuits, and that's where Eli the Iceman really comes in.
Okay. I was like, these concepts I'm partially understanding, but we haven't spoken on anything like this. And
Yeah.
he got excited and
Yeah,
talked for 2 hours. So
2 weeks, and Eli the Iceman will be fantastic. It's a wonderful mnemonic device, but it means less than nothing to you right now.
yes, sir. Okay.
Anything else?
Not for me.
All righty. So unless anybody else has anything, I will talk to you guys on Monday.